Years ago, he's now a graduate student at the University of Maryland. And so he's going to talk about some of his current research. So I'll let him do the rest. But thanks for coming out here, Nate.
No problem. All right, I'm glad you guys could come. Hopefully it's kind of interesting. It's not too much math, so don't be scared of that. So I'm Nate. What I did this summer, I'm going to talk about what I did this summer, what I'm currently working on down at UND. So I had an internship down at Tucson River Naval Base, and we did some optical, where we were shooting lasers through some water to see how the lasers would scatter. So I'm going to talk a little bit about beam propagation through a general medium. So in this case, it's going to be air and water. I'm going to go into, well, what is scattering theory, how are we going to quantify light getting bounced around by particles. And I'll talk about two types of laser beams that we use, and then I'll get into the measurements, and then what I'm currently doing with the atmospheric scattering. So most of the stuff is going to be two parts. One was the water, one was air. So the first part I want to show you guys is when you shoot a laser through the atmosphere of water, there's a different attenuation for both of them. So you can see here, this graph is showing absorption for different wavelengths. So you can see in the visible range from about 500 or 800 nanometers to a little bit into the far infrared. You can see you've got really good transmission through those areas because the absorption is low. So what I'm trying to show here is that these are the wavelengths that we're going to be using through propagation through air. And then here, it's a different graph, but it's the same concept, is that at around blue light, green light, the laser goes through water further than it would if it was at a ultraviolet wavelength or in the infrared, which makes sense because water is blue. You shot a blue laser through it, it should go further than a red laser. And then the thing, I couldn't find the graph that I had before, but in the open ocean, blue wavelengths travel further than any other, and then in murky water, green is more or less the laser that we're going to use. And then that's the laser that I used in my experiments because we're doing this mostly off coasts and next to the shore. We're not really worried about open ocean stuff right now. That's what I wanted to show you, for basically why I chose the wavelengths I did later on. So the application for this right now is in atmosphere. You've probably heard of autonomous vehicles. They do the ranging by using LiDAR systems. So this is pretty important, and we have to know how the beam propagates through the atmosphere to make good LiDAR systems. And there's also LiDAR that we use in the open ocean. It's the same concept as if it was in air, but in this case it's just through water and not air. We use undersea imaging, radio-finding communication. So undersea imaging is you basically have a laser, you shot it back and forth really, really fast, and you can map the image. Normally you get it in black and white, it can't get color. But we can use that for detecting, you can map the seabed, this is how the seabed's mapped, or maybe detecting mines if you're interested in looking for weapons. Range finding, same thing as the LiDAR. And communication, so the idea here is you can use light for communication. You guys probably heard of fiber optics. It's the same concept, you can do it in free space, and that's the idea here. You have a submarine come up next to a ship, and you can use light instead of radio waves, since light has a higher bandwidth, so you can carry more data. And if you just pull up right next to the ship, you can send high data rates in a very short period of time. So if you need to unload a lot of data, it's pretty good for that. And then short range through space communication. This is kind of what I'm kind of building towards. Is we're more interested in to use light just through air for short range communications. This would be applicable for the military if they're trying to get through looking for fire support or something like that. Most of the stuff is military applications as of right now. It's kind of disappointing, but oh well. So what we need to know if we're going to do this effectively, we need to know how does light go through the atmosphere. So there's one or two things here that we'll be focusing on, which is scattering. Absorption and scattering are the two biggest issues with trying to get the beam to and from the target. So this picture here is showing that if you transmit a beam through the air, you run into absorption. The particles absorb the light, particles scatter the light, and then you hit your instrument, or not the instrument, you hit your target that you're looking at. And then you also back scattering, you got the same absorption scattering, and the same issues going to and from. So we need to figure out how does the light scatter to do this effectively. because the graphs I showed before were already trying to minimize the absorption of the beam going through water. So the last effect is going to be scattering that we're worried about. So the simple way of doing it is a beam propagates using Beer's law. So you may have heard about this in chemistry, as you guys did in spectroscopy. What happens is when the beam is going through the air, it decays exponentially relative to whatever the incident power is. So this is going to be true if I put in, 1 watt beam, 5 milliwatts. It's going to decay exactly the same. And the dependence on the medium comes from this right here. So this B value is called the extinction coefficient, or total extinction coefficient. So I'm going to be talking about this for pretty much the rest of the lecture. So it's going to be the extinction coefficient, which is the number density, as shown here, times the scattering cross-section. So scattering cross-section is kind of a weird thing. I'll talk about that when I get to scattering theory. And that's pretty much it. So we're interested in basically trying to find this number here, okay? And this number changes depending on the index or refraction of the particle. So when light goes through two different surfaces, you can see, if you look into water, the light kind of bends. That's because the index or refraction is different in water from air. And the idea is the extinction is dependent on the index of refraction and also the complex index of refraction, which I'm not going to talk about at all because we're assuming particles have a real index of refraction in this case, which means that the extinction coefficient is only going to be from scattering. If there's a complex number there, it would also have some attenuation, only going to worry about scattering. So what is scattering? Scattering is if you have a incident beam coming in, most of the time we talk about plane waves, which means the electric field and B field are perpendicular to each other. That may mean nothing to you now, don't worry about it. That's not really important. Well, actually, I'll take that back, I'll get to that. The next part is basically if it hits a particle, let's just think, when I say particle, think small, think 10 micron particles, 50 micron particles. These things are very, very small. And think about that when I'm talking about a particle. So this little thing here, you can say 50 microns in diameter. And what happens is the light hits the particle re-radiates the light as a spherical wave. So you can see here, if this is in 3D, it's going to be like a bunch of little wave fronts coming out from the particle. So you got a plane wave coming in, hitting it, and then you've got forward scattering, back scattering, which is just a fancy way of saying the light that goes, in the same direction as the incident beam, and light going back from the incident beam. And scattering angle is going to be relative to the axis here. Scattering angle is going to be the angle that the light is scattered in this direction, this direction. So this would be like 90 degrees, 45 degrees. So that's when I get the scattering angle. The difference really is absorption is when light hits the particle, the light is absorbed, so it's changed to thermal energy or chemical energy in the particle. And scattering is the way the particle gets excited, and then when the energy state goes back, it re-emits the light in one of the few directions. That's pretty much it. And you can think of it like this too. So in foggy, well, we'll get to foggy weather. So that's what scattering is. And next part is, well, how do we quantify this phenomenon? So you've probably heard of Rayleigh scattering, which is why the sky's blue. So in this case, Rayleigh scattering is when the wavelength of the light is much bigger than the diameter of the particle. And in this case, Rayleigh scattering is looking at particle diameters of like nitrogen, oxygen. So they're even smaller than 50 microns. They're a few nanometers, picometers across. So that's Rayleigh scattering. So what you can see here is Rayleigh scattering is pretty much the same scattering in all directions. But when you get to bigger particles, we can't use the approximation of Rayleigh scattering anymore. We have to use Meade scattering. So Meade scattering is more prominent if you're driving down the road in foggy weather. You can see when people have their high beams on, you get all of this light scattered mostly at you. There's not much going in the other direction. That's because Meade scattering is very peaked in the forward direction. So that forward scattering I was talking about, it's going to be a lot greater than any of the other directions. And we'll get to some graphs that show that. And then as your particle gets bigger and bigger, the forward scattering gets bigger and bigger. And then this is a picture from the summer. So this is showing a laser beam going through 50 micron beads. So there's a little vial of water in front of it, and the laser hits it. And this is the scattering pattern you can see from some distance away. And so this is kind of what I'm gonna quantify this. How do we quantify this picture? And the other thing, you notice it's green light, 532 nanometers, because that's what beam we're interested in. And that's also the same laser, or the same wavelength if you had a green laser pointer, same laser, just higher power. That's pretty much it for me scattering. So I'm going to be focusing on the me scattering regime for the rest of this talk. The next part is this thing called a phase function. So I don't know, it's called a phase function because of astronomy. It's kind of weird that it carried over from astronomy, but that's why it's called phase function. And phase function is just a fancy way of saying the angular dependence of the scattering. So as you can see these graphs, you've got different angles from 0 to 180, where 0 is going to be forward scattering, 180 degrees is going to be your back scattering. Okay? And you can see these are some graphs for 5 micron particles. As you can see, there's a little bit more peak in the forward direction. Not that much because it's a smaller particle. If I were to change this to 50 microns, this peak would be a few orders of magnitude larger than the rest of the scattering. And then you can also see, this is for a single particle. Keep that in mind. There's a strong dependence on the polarization of light that comes in, and that becomes important later on for when we travel through air. You can think of it as this part here is normalized so that the light, this scattering is not dependent on a solid angle, so it's how much light is scattered in each radial direction. If you think of a sphere, if you take like a point coming out of the sphere, it's how much light is scattered in that one area, not all around it. And it's used for LiDAR prediction models because you need to know how much scattering is in each direction. So if you were to run code on trying to figure out how LiDAR works, you would have to use this type of function. So now that we have a little bit of background on what I'm going to talk about with scattering theory, we're actually going to talk about it going through water. So what we were trying to experiment with this summer was the difference between propagation of helical beams, so these fancy things, and regular Gaussian beams. So the Gaussian beams pretty much in any laser that you see here. It's very, the intensity is highest in the middle and it falls off as you go out. So if you have a laser pointer, that's all a Gaussian beam. And what we want to see is this helical beam. So I talked about the wavefronts where E and B, the E field and B field are perpendicular to each other in the same plane. So here you can see the E is pointing up, B is going this way, propagation is going this way. So that's what this is talking about. Here, your E and B field are now spatial. They've got spatial dependence. So as it propagates, the E and B field are kind of falling in on themselves. So if you're familiar with helixes, it's basically a helix. So if you've done that in Calc 3. So there's been a few new ways to create this beam. They came out with these things called phase plates, which are going to be a bunch of materials stacked on each other, that then when the light goes through it, it changes the phase front of the wave as it goes through these stacks of plates. So you get this helical kind of shape. This carries something called angular momentum of light, which is a very different phenomenon compared to just a standard Gaussian beam. And these are what the spots look like. So if you shoot a laser with a helical beam, you have this kind of donut in the middle. And we want to see, does this change how the light scatters? And that's what I ended up doing this summer. So I just got to shoot lasers through some water. It was pretty fun. And what we're trying to figure out is, there was a NASA paper where they did some simulations on trying to see how optical vortex beams travel, or when they hit a particle, how does the phase function look? So the phase function, this is the same graph as I was showing before. It's angle, normalization, but you can see, this is for a single particle, let it be, that you can see at small angles and at backscattering, the intensity of the light basically goes down to 0. So their conclusion was that if you have an OAM beam or a helical beam hit a particle, you don't get much scattering in the forward direction and the back direction, which would be good because then you don't have as much scattered light to worry about when you're trying to detect an image or something like that. So that seems pretty good, but we don't know if this was true because there haven't been any experiments done yet to test this hypothesis. And you can see here, as you change the order of vortex, you get a lot less scattering as you go higher in order. So the order that we used in the experiment was L is equal to 16. So this should be pretty small down here. And we just wanted to see what would happen. As you can see, this would be for a regular Gaussian beam. These are the vortex fields. So we go into doing this, and the experimental setup I used was pretty straightforward. You got your laser, you got some optics to expand the beam, so I wanted to get a bigger beam size, so I hit more particles in the water. And then the water cell, well, contains the water and whatever beads I'm looking at. So in this case, this picture was done with 50 micron beads. This one was done with, I think, 3 micron beads. So, and then there's some optics here that I get rid of here, which isn't very important. But, so this is 50 micron beads. We're measuring very small angles. If we want to see, I didn't show the graph for 50 microns, but 50 microns, like I said before, there's more forward scattering, and you got a bunch of really prominent side lobes around 0 to 2.5 degrees. So this is measuring from 0 to about 2.5 degrees on that phase function. This one can measure from 0 to 90. So when we use bigger particles, you get more side lobes that are out further than when you've got bigger particles. The side lobes kind of scrunch up at the smaller angles. So that's why we have to go out further to measure the different angles. As you can see in this picture, I can go back to the other one, but there's a lot more side lobes here that you see compared to here. You've only got 3 or 4, and this is about, out here is about probably 45 degrees. So we had to change up how we measure that. And pretty much, I just sat there. This one, luckily, was motorized, so I made a program for it, hit run, and it just goes back, takes data. This one, I had unfortunately do manually. So I'd sit there moving that thing, go back, take data, go back, take data. And that took about probably 30 minutes to take one measurement. So, yeah.
Which language did you program in?
It was in LabVIEW. Yeah, LabVIEW was how we communicated with the little motorized base here. Yeah.
I have a question. So you say two like direction, like they have the same angle but different directions. Do you break that down as like the same angle? What do you mean? So if they go in two separate directions, but if you take it from the side, they both have the same angle.
Yeah, so are you saying if I come in and hit the white light, and then if I have some light go this way and light go this way, is it the same angle? Yeah, it's going to be the same angle, since we're assuming phase functions, like here for example, this would wrap around from 180 degrees to 360 degrees, and that would be your full view of the scattered light. We don't, because this is symmetric around that, we only take 0 to 180. That makes sense?
Question, did you have trouble with repeatability when you had to do it manually?
No, actually. There was when I first did it, I just had a string on the mount, and that was not repeatable. So I found a nice metal rotational stage, and that thing I could change it very accurately to probably a millidegree, and then I could just lock it in place when I get back to that point, and that was pretty repeatable. Does that answer your question? So that's the experiment that I did. The data, so this is for 15 microns. So this is the small angle measurement from this setup. So this one, you've got the green, which is the theory. So that's the phase function stuff we talked about before. That goes up to about 2.5 degrees. The red is the Gaussian beam. Blue, which now let's think about, that was a bad choice. But the blue, if you can see it, is the OAM beam. So you can see that now the OAM beam, we predicted that there should be less forward scattering, right? Since we kind of went to a null on the phase function. There's no null. And this is at very small degrees. And that null is around 0 to 5 degrees. We don't have anything that's different. So that's one conclusion, but we're using big beads. We're using 50 micron beads. But the paper used a beam size, the OAM beam size was only 5 microns. So we need to try and figure out how to get the same paper conditions to the experimental conditions. And this was not that case. So this really is still not answering our question. next results, this appeared in almost all my data. This is for the phase function of a 3 micron bead going through for the second experiment. And as you can see, you measure out to about 90 degrees, which was expected, and you can see the different lobes. So the OM beam and the Gaussian match up pretty well to each other, but they don't match the theory very well. I could not figure out what this was from for the whole summer. It was very annoying. But I guarantee that that's from me not aligning the system correctly. So somewhere along the way, I wasn't calculating the angle right coming out of the glass, or me just not being consistent with measurement. But that's here or there right now. Unfortunately, that's what we got. But you can still see this is for 3 micron beads, so we're getting down closer to where we want, where the bead is the same size as the bead diameter, and you still don't have any difference in the forward scattering. So that's another conclusion that we came to. But the next part is, so I don't have any data from the last experiment I did. The last experiment was, we focused the beam down to 5 microns, put 5 micron beads in there, and then we wanted to see if the scattering pattern was any different. And even when we did that, which is the same conditions as in the paper, we saw no difference between the OAM beam versus the Gaussian beam being focused to that size. So we basically came to the conclusion that it's really no different going through the OAM beams versus Gaussian beams. There's no difference going through the water. So you can use the same scattering theory for both types of beams. And the next part that we wanted to do though was get a single particle. So put it on some type of microscope slide, evaporate the water, and then align that with a beam. So we get one bead, hit it with the OAM beam, and see if we get that actual phase function that they predicted in the NASA paper. And this I did not get to do, but that would have been a pain, trying to get one little bead and then aligning it with a 5 micron spot size. The beam is very, very small, the bead is small, but that's something that they're continuing with down there right now. And that was pretty much it for the summer. So this wraps up the water propagation part. So now my work, which I'm doing down at UMD, is I'm doing the same exact stuff almost, but through air. So the only difference is the index air fraction of what I'm looking at. And I'm also not looking at polystyrene beads, I'm looking at aerosol particles. So now comes into the question, we gotta pick, well, what are our aerosols? So from looking through the literature, the most agreed upon distribution for aerosol particles is this modified gamma distribution. And the issue is for different types of air that we're looking at, or different scattering particles in the air, they've got different radii. So here, this is what we're looking at. We're looking from haze particles to fog droplets. So my distribution will have radii between 0 and 40 microns, which includes haze particles, fog droplets, but no rain, snow, or hail. As you can see here too, when you're at these types of radii where the wavelength is close to the particle diameter, you use scattering, and then Rayleigh scattering is when you get to really small air particles again. But if we get too big, it basically becomes a problem of the geometry of the particle that we're looking at. And this is what I want to get at too, is with distributions, instead of looking at a pure solution of one particle, your extinction coefficient changes. This is what it was originally, where it's the area times the number density. So the number density is just how many particles there are per cubic meter. So that scales what your attenuation is going to be. And then this thing called an extinction efficiency. So how well does the particle scatter the light, or how well does the particle absorb the light? But in this case, we're only looking at scattering. For a distribution, you have to integrate over all the cross sections, or the extinction cross sections for all the different radii. That's really the only difference between using a distribution and looking at single particles. So this is a problem that we have to figure out how to model the air correctly. And so what we're trying to do is we're making a visibility meter. So the idea is we measured forward scattered light independent of the distribution of particles. So that's kind of a weird thing to do, but the idea is if you have different distributions, so this one here is for the smallest radii that I'm using, which is 0.01 microns. And then the top one up here is for a bigger particle of 40 micron radius. And as you can see, as you increase the particle size, you get more scattering in the forward direction, which is expected for B theory. And what I'm doing is I'm trying to find out where the phase function for these different radii is most linear with respect to angle. So I'm like taking cross sections from here, going up here, and then I fit that to a straight line, and then we figure out where our angle is most linear. And it falls somewhere between 30 and 40 degrees. And this is found in a few of the papers that I'm looking at, so I'm on the right track with the code. And that's pretty much what we're looking at there. And then the idea is, once we find that angle where the phase function is most linear for the different distributions, we have to go and figure out, well, can we extract the extinction coefficient from this information? And from here, we use phase function values. So this is normalized to whatever the maximum is for each of the phase functions. And then we're plotting the extinction coefficient for the different distributions against the phase function value. So we're trying to figure out, if we were to measure the phase function value at a specific angle, where would it be most linear for the different distributions in terms of extrapolating the extinction coefficient. So if I measure a phase function angle, and if there's a different distribution in there, it should lie along some line to find the extinction coefficient. It's kind of weird. Every time I explain this to people, they never seem to understand what I'm doing. It's very weird trying to extrapolate extinction from a phase function value, because it's not really what comes out of the theory. You can't do that like perfectly. And what I'm trying to do is find where the angle is most linear with extinction coefficient. And this is the best I could come up with as of right now. I'm aiming that this should also be from 30 to 40 degrees. As you can see, that's not quite true. I've got best agreement of about 10 degrees to 40 degrees, or 10 degrees and around 40 degrees, which is not what I'm looking for yet. So I've got to go back to the code, figure out what's wrong with my code. But the experiment that I'm doing right now is this. So you've got an LED at 940 nanometers, because this is, we're looking, if we go back to the air, the absorption graph for the air, IR travels further down than some of the other lasers that we're looking at. The other thing too is, because of the size of particles that we're looking at, we picked 940 because its wavelength is corresponding to the particle radii. So they're on the same order of magnitude. And what we're looking at is, we basically put a photodiode here. This is the scattering angle that I was talking about from the data before, at 35, roughly 35, well, the theory is saying it's roughly around 35 degrees, so I stuck one at 35 degrees. So I'm gonna try and take some data and see if I can get my best fit, my extinction coefficient line, to match up with my data. And then this is pulsed, so I don't have to worry about too much interference, like background interference of Rayleigh scattering or other light, because I know when my data is good, because this thing is going on and off at some frequency. And then, yeah, we convert the data, and what I'm getting to next is basically, this is what some of my first data looked like. It's not that great. You can see there's a 60 hertz thing going along, so obviously I've got the power in my data, which I have to get rid of. And as of right now, I'm still trying to build the device so I can take it out and test it in different areas, different conditions, so like fog, haze, rain, and trying to figure out where is my discrepancy in the theory versus my experiment. So that's pretty much what I'm going on now. As you can see, the extinction coefficient is around 2.5 E negative, so 0.00025 per kilometer. So that's how much of the beam is attenuated per meter. That's how much of the beam is attenuated per meter as it travels, which is good for clear conditions, but I'm still not trusting my device yet to say that this is the actual extinction coefficient for in the lab. The biggest problem we're running into now is, how do you trust your measurement? And this is a big deal, because if you just take one type of measurement and you don't change anything, so in this case I can change the wavelengths of my laser, I can change the angles I measure, I have to make sure my data agrees for different angles or different wavelengths. So at this point in time, you have to figure out how to make your experiment, trustworthy. And that's what I'm running into now, and that's pretty much where I'm at this point in time. But that's pretty much all I got. So Any questions? Yeah.
So you specified you're using like the water, or in the air. What, and you weren't really like doing open water, like testing, like, is there like a depth, like, you're using, like, to test the light?
So the depth it was a little vial that was maybe 5 centimeters across. What we were looking at was more, how does the light scatter when it goes through water, not over a distance, because as it goes through
But
water.
like the depth in the surface area would like make an, impact, right?
Are you talking about for the beads? Or
Yeah.
just so the beads, not the.
Well, just in general, I mean, just like what you're like actually like what component you need to like test it. Like, like what type of like object you're like testing, like the water.
So in the water there are little beads, and it doesn't matter the length of the water.
Oh, you have beads in the water.
Yeah, there's beads in the water. That's the scattering beam that we're looking at. Actually, to answer that is these phase functions, everything I did is in the single scattering regime. So it means we're assuming that the length and the amount of beads in the water is less than 1. So the scattering coefficient times the length is less than 1. So yes, it does matter what distance and what we're looking at.
Yeah.
If we have a longer distance, all these approximations pretty much go away
Yeah.
because you're doing multiple scattering. So when you hit, if you've got like this much length and the same amount of particles is in this much length, you have to account for all the scattering with these different particles, and then you have to sum up all the different phase functions at the end. So that becomes a harder problem to solve, and it's harder to do that experimentally. You can do it with a computer program pretty easily, because that's what the guys did at NASA. But if you're just looking at the experiment and trying to match it to mean theory, you gotta be in single scattering.
Okay.
Does that make sense?
Yeah, now it makes sense.
Okay. Yep. Any other questions?
Can I ask about the helical versus the Gaussian beams? So you said that the results you found was that there was not an appreciable difference, at least on the measurements you were using. I mean, was this disappointing in terms of the hope had been helical beams would provide more focused scattering in one direction, or?
Well, that was the conclusion that the NASA paper came to.
NASA had the same thing.
It was a very quick conclusion to make, because they had very confined parameters in their code.
Right.
It's not really a disappointment. It would have been. It's not. That would just be a bonus part of using helical beams. In the case of using helical beams, they want to use spatial multiplexing or coherent detection. So coherent detection is for only light that stays coherent through the scattering medium. It will stay in that helical shape.
Okay.
So then at the receiver end, you can turn it back into a OAM beam, and only the light that would stay coherent originally will go through the OAM. The scattering light will go away. So
Okay.
the scattering at the different directions is kind of just a bonus.
Okay. All right.
Yeah.
How do you know that the air, okay, you did this, when you did the University of Maryland in air, how do you know the air was the same from one day to the next?
It's not.
It's not.
It's not going to be. The idea is we measure the extinction coefficient, or the extinction coefficient, as a function of time.
Right.
And as time goes on, the extinction is going to change.
Right.
So no
So
matter.
it's normalized. So that's how you normalize it.
Yeah, so the other thing, I'm taking into account all the different aerosol distributions for haze, clear air, and fog. And I'm trying to figure out, for all those different distributions, where can I measure scattered light and come to a general conclusion. It's more of an approximation, not an exact.
Some days it's, even with fog, it's more foggy than other days, right?
Mhm.
Not all fogs are equal.
Well, all we need there is, if I do the measurement, I need to see that the extinction coefficient on a very, very foggy day is going to be a lot more than if it was a less foggy day.
I see.
So that's basically what we're trying to look for there. So that's not necessarily meaning that there's bigger particles in the fog. It may just be more dense. So my number density is going to change, and then that increases my attenuation coefficient. Is that?
Thank you.
Yeah.
Can you chalk your beam here?
Yeah. So this is all.
So, like, do you have a
Oh, no, yeah, we don't have a chopping wheel. It's just, I'm using an LED right now. I want to use a laser, because lasers have less beam divergence, but I'm just pulsing it on and off with a MOSFET.
Because I think if you chop it, you could probably mask the 60 hertz.
Yeah, I gotta do that. I mean, this is chopping it so that, I'm able to figure out what light is from my diode at the detector. To get rid of the 60 hertz, I'm making PCBs for this to get it off of breadboards, and hopefully they get rid of some of that. But I'll talk to you about that. Okay, yeah.
So, I'm just wondering, like, how did you choose these subjects specifically for mine? You know, I really want to know, like, why you chose them, because, like, if I was told that, okay, no subject, experiment, then I would have no idea. Like, top of my head, I have no idea.
Mhm.
So, yeah.
Well, the subject kind of came because I was looking for an internship, and it was in optics. I was looking for something in optics to do, and then I talked to my advisor down there, and he was looking for somebody to do a project like this. So it kind of fell on me more as I had to look for something, and this is what I ended up working on, versus something I picked. But that's because I was looking around for an advisor at the time. If you're, I don't want to say desperate, but if you're looking for somebody to work with in a short period of time, you kind of take whatever you're given. And I was looking in optics, stuff like that. So this is what I did in optics. Now, if you're looking for something that's very specific to what you want to do, you gotta look far ahead of time. But it also depends on where you go to school and who has openings at the time. That really dictates what you might work on and what you're going to work on for a degree. So, does that answer your question? Anything else?
Thank you, Nate. Thank you for coming. We appreciate it.